Swayam Prabha. Digital India. Educated India.
So welcome back. In the previous lectures on interprocess communication, we had seen a number of issues relating to what might happen when a number of concurrent and cooperating processes they are running on a processor. Okay. We talked about the critical section problem, we looked at a number of solutions to handle the critical section problem. Then specifically we talked about some applications, classical applications like the producer consumer problem, like the readers writers problem, like the dining philosophers problem, where we saw that there are some problems that arises due to the concurrent nature of the processes which are running, and we also suggested some solutions. Now, today in this lecture what we shall be looking at? We shall be looking at some specific code snippets in Linux. So, here we shall see how, if we are writing a program ourselves in C, how we can do a number of the things that we had discussed in the class. So, we shall be looking at some of the useful features that are there in the programming languages like C or C++ or in other languages also, and how they relate to whatever we have discussed so far in the classes. Okay. So, let us look at some of the Linux code snippets. We start with something called creating shared memory segments. Now, here what I would like to say is that when see earlier we talked about the critical section problem, mutual exclusion problem, there was a common problem arising there. Two or more processes were trying to concurrently access or update some shared memory location or shared variables. Because of that, the critical section problem was coming. Now, there is one assumption which is inherent there, is that there is some shared memory or there is some shared resources. Now, talking about processes, suppose there are two processes. So, where are the shared memory and shared resources? So, here we shall be seeing how two different processes can share some common memory locations, and one process can write something into that location, another process can read from that location. So, there we can create a scenario where whatever we are talking about, the critical section problem, the mutual exclusion problem, they can come into the picture. Okay. So, let us see how shared memory segments can be created in Linux when some processes are running. First, let us try to understand the mechanism pictorially. Let us say we have two processes P 1 and P 2 which are running, and these are concurrent processes. So, one process is P 1, other process is P 2. Now, one thing we discussed earlier, if you recall, that whenever a process is running, it occupies some space in memory, and the typical spaces that are occupied, they are split into some regions, like there is something called text region, data region, heap region and stack region. Similarly, for the process 2, there will be similar regions. Now, I also mentioned that whenever you create a new process using the fork system call, to start with, the text region are shared, but subsequently if you execute one of the exec family of calls, that text region will be overwritten by the text region corresponding to a new program. So, it becomes totally separate. So, on the right side, let us see, suppose this is a snapshot of the memory we see, and all these 8 regions we have shown for the two processes, they are allocated some space in memory. Now, we shall be seeing later that when space is allocated in memory, they need not be allocated in contiguous locations. For example, process P 1 may be having the text region here, it may be having the data region here, the heap region here and stack region here. Okay. Similarly, process 2 may be having the text region here, data region here, heap region here and the stack region here. Now, we are talking about something called shared memory or shared memory segment. See, in the picture that I have shown here, there is nothing shared by among the two processes. All the 4 regions occupy separate spaces in memory. So, there is no mechanism by which P1 can write something and P2 can read that data. It is not possible, because they are allocated separate spaces in memory, and later on when we shall be talking about memory management, we shall be seeing that there is a adequate protection mechanism also in place, that one process cannot access the address locations of another process. Okay. So, let us see. The first step here is that a shared memory segment is created. That is the first step when you want to create a shared memory portion or a segment between two processes. So, we create a shared memory segment. So, it gets created in memory. There is a memory location. So, we are defining it as a shared memory segment that gets created in memory. But right now, the processes P1 and P2 are not aware of that. Okay? They still do not have access to that shared segment. So, next what happens is that these shared segments are attached to the processes P1 and also to P2. So, after this attachment is done, what will happen is that if you see, the process P1 will be having a 5th region, process P2 will also be having a 5th region. The difference of this region is that both of them are pointing to the same location in memory. Unlike the other regions which are totally separate, this shared region, they are attached to the address space of both the processes, but they refer to the same data block in memory. Okay. So, after we attach it, you can understand if the process P1 writes something into that shared region, process P2 can also access the same region, right. Process P2 can also write, process P2 can read, so whatever they want. So, the region is totally shared among the two processes. Next, when the processes are done, they do not need that shared memory anymore, they will be detaching that shared memory segment from their address space first. So, that 5th region which was attached, they will get detached. But at this point in time, still in the memory, that shared memory segment is residing. That part in memory is still there, but from P1 and P2 we have basically removed them. So, P1 P2 cannot access them anymore. Okay? Fine. And lastly, the shared memory segment is totally removed, which means from memory also we are removing that and we are freeing up the space which was occupied by the shared segment, right. This is what is happening. So, conceptually this is how shared memory segments are defined, they are attached, they are detached and they are removed. Now, let us see with a example program how in C we can do this same thing. Okay? Let us look at a real code written in C. But before going into the code, let us look at some of the function calls that we shall be making in the code, which are related to shared memory. The first function call is called SHMGET, shared memory get. So, what SHMGET is actually doing, it is creating a new shared memory segment in memory. So, as I said using that diagram, a shared segment is getting created in memory, and there are some parameters in this function call you can see. This key is supposed to be a unique integer, it identifies that shared sequence number, okay. And 50 is the size of that shared segment, how many bytes. If I write if here I write 50, it means I am allocating a space equivalent to 50 bytes. Okay. And the last parameter IPC create or 0666, these are some constants which are defined in a header file. IPC create means if the shared segment is already existing, do not create it. If it is not there, create a new shared segment with this key value. And 0666 means what kind of access permissions you are giving for this shared segment. See, in Unix, for protection you may be knowing that there are 3 groups: user, group and all others. And in every group there are 3 bits: read, write, execute. And this 666, this is an octal number. 6 means 110, this means 6, which means I am giving read and write permissions, I am not giving execute permission. So, there will be 3 such read write X, and I have given 666. So, this is also 6, this is also 6. The first group indicates the user. Suppose I am the user, for me what are my access rights? This is for the group, for all users who belong to the same group as myself, and the last 3 is the others, all other users. So, I am giving read write access to everybody, but if you do not want, you can have something else written there. Okay. Now, the second thing is that after creating, we are attaching the shared memory segment to the process address spaces. So, you see, when shared memory get is called, it returns a pointer, an address, SHM ID. SHM ID is like an ID which identifies that shared memory segment in memory. So, later on when we attach the shared memory segment to a process, we make a system call called SHM80. Okay. Here we use that same shared memory ID which was returned by SHM get. And the other 2 parameters you do not have to worry for the time being, we have to give null and 0, but there are other reasons also, I am not going into that detail. And when you are done, when you want to detach the shared memory from a process, just call SHMDT, and this SHM80 returns an address, a pointer in memory, my shared. So, when you are detaching, you have to specify that address. And finally, when you want to totally remove that shared segment from memory, you have to call SHMCTL, shared memory control. So, you specify that same shared memory ID, you specify a value IPC RMID. IPC RMID means remove this object, in this case it is a shared memory segment. Third parameter, do not worry, it is null. So, let us see the program now. Using these function calls, we have written a program. First thing is that you have to include some header files. Well, stdio and strings are very standard, but there are some new header files which also we are including. IPC stands for inter-process communication, SHM stands for shared memory. So, we have to include such shared file, and some of the data types like here PID T, key T, these are all defined in this SHM.h in this header file. Okay. So, we are defining some variables in the beginning. We are defining a PID, basically an integer. PID T means basically an integer, shared memory ID, key is also an integer, key T, it is a name it is given, type definition, and a pointer called my shared. And I said key has to be unique. Well, here we have given some unique number 7755, let us say. Okay. First, we are creating that shared memory segment in memory using SHM get. So, we are calling as usual key 50 bytes IPC create or, and the thing is that if due to some reason the shared memory cannot be created, the function will be returning a negative value. So, it is a good practice to check whether the value returning is negative or not. If it is negative, you print an error message and you stop. Return 1 means your program will stop. Okay. After that, let us create 2 processes. Let us call fork. So, a child process will get created. Now, you recall when fork is called and a parent and a child, both of them are running. So, for the child process, the value of the PID will become 0, and for the parent process, the value of the PID will become the PID of the child, which means some value greater than 0. Okay. So, again after fork it is a good practice to check whether PID is becoming negative or not. Negative means due to some reason the new process could not be created. So, again you can print an error message and you can stop, return 1. Otherwise, you check whether it is the parent or the child. If it is a parent, which means you can check PID equal to 0, then you do this. Otherwise, PID is not 0, it is the parent, you do this. So, in the child what we are doing, you see, just for the sake of illustration, we are attaching the shared memory segment, okay, and in the shared memory segment the address is my shared. Okay. We are copying a character string hello there to this shared memory area, and in the parent process, parent will be reading that value, okay. And after it is done, you are detaching this from the child process. So, child process is attaching that to its own address space, copying some string to that common area, and then it is stopping. But the parent process what it is doing, it is again similarly attaching it, but remember this my shared for the child and my shared for the parent, they are separate because they are located in the data areas of the two processes, data area or the stack area, they are separate. Okay. And now, the parent is printing the value of my shared from the shared location. So, it will be printing hello there. You see, after hello there, it is waiting for 4 seconds. Just you can change this time and see what happens. And here again it is printing, it is detaching, and finally, it is totally removing from the memory. This is a very simple example using shared memory, which shows how these 4 steps can be performed: creating a shared memory segment, attaching, detaching, and deleting. Okay? Fine. Let us move on to the second kind of inter-process communication mechanism that I want to talk about. This is something called pipe. See, pipe, you have seen the conceptual analogy of a pipe through which you can pass water, you can pass some gas, anything, steam. So, normally whatever you are passing flows from one end of the pipe to the other end of the pipe. That is how a pipe is defined, right. So, here conceptually it is very similar. So, a pipe is conceptually looking like a normal pipe that you know about. In C, when you define a pipe, we have to declare an integer array of size 2, int my pipe 2. So, there will be 2 array elements, my pipe 0 and my pipe 1, and normally what you do is, let us say some process P 1 is here, some process P 2 is here. The process P 1 will be writing something to my pipe 1, and process P 2 can read something from my pipe 0. So, my pipe 1 is the end where you are writing, my pipe 0 is the end from where you are reading. So, because it is like a pipe, whatever P 1 is writing, P 2 will be reading the same thing in the same order. So, using a pipe, 2 processes can also communicate among themselves. One process can write something, other process can read the same value, right. This is possible. Let us see how it can be done in C again. So, we are showing a program. This program is relatively much simpler as compared to shared memory. Here again, well, I am not showing the header file. So, here also header files will be there. We define a PID for a process, it is of data type PID underscore T, that is defined in the header file ipc.h. Okay. Now, let us get ready for creating the pipe. For that, we are creating this integer array, as I said, we call it my pipe of size 2, because at one end we will be writing, at the other end we will be reading. My pipe 0 will be writing, my pipe 1 will be reading, and there is a integer variable n bytes we are defining, and a character array message we are defining, where some example message we are initializing, test message to send, and we are defining a character array called buff of size 50. Now, when you declare mypipe 2, automatically it is not the case that one process can write into mypipe 0, other process can write into mypipe 1. That will happen only after you execute a pipe system call. So, whenever you call this function pipe, then only the pipe gets created. Conceptually, this pipe gets created. So, at one side you can write, at the end mypipe 0, other side you can read, at the end mypipe 1. Okay. Now, you have created a pipe, and we have also created these two things, mypipe 0 and mypipe 1, mypipe 0 and also mypipe 1. These are two variables. Now, what we do? We are doing a fork to create two processes. Again, if it is negative, we print an error message, fork failed. Otherwise, PID 0 means this is the parent process, child process, 0 means child. You see, the child process will be writing the message into the pipe, but there are two variables, mypipe 0 and mypipe 1. As I said, to write, you will have to write into mypipe 0, write into mypipe 1, read from mypipe 0. So, what the child is doing? It is closing mypipe 0, because it is not requiring mypipe 0. So, it is writing into mypipe 1. Write is a function call again, using which you can write into a file. Mypipe 1 is like a file. You are writing this message, test message to send, and string length message, how many characters are there, and you may be knowing the last character of a string is the null character. So, there is a +1 including that null character. So, you are writing the whole string into one end of the pipe, and you are exiting. So, you are writing into mypipe 1. Let us see what the other process is doing, the parent process is doing. The parent process will be reading from mypipe 0. So, it does not need mypipe 1. So, it is closing mypipe 1. It calls a function read, from where it can read from mypipe 0. After reading, where it will keep? It will store in the array buff, which we have defined. We have defined it as a character array, right? Character buff 50. And this is the maximum size of the message you are also specifying, size of buff, which will be 50. And whatever value is read, you can print it out, receive string %s the value of buff. So, you will see whatever message the child process sent, the same process is coming back here. So, this simple example illustrates how using two or more processes you can carry out inter-process communication. So, one process can write into a process, write into a pipe, another process can read from the pipe. So, in general in a program you can have any number of pipes depending on the number of processes you have and the number of kinds of data it wants to share. And one characteristic of a pipe is that it is a strictly first in first out kind of a structure. Whatever you are writing at one end, in the same order the data will come out from the other end, you can read from there, right. Suppose you try to read something, but at the other end no one has written anything as yet. So, you will have to wait. The process that is trying to read is going to the block state, it will go to the block state, it will remain there until or unless someone writes into the pipe. So, you see when we had earlier talked about a process going from running to the block state, there are so many reasons why a process may need to go to the block state. This is one reason, that it is trying to read from a pipe, but there is no data in the pipe yet. So, it will has to wait, it will go to the block state. Okay? Fine. We talked about mutex locks earlier. We talked about threads, we talked about the pthread library, how we can create threads using pthread, and you had seen, you recall, using pthread library you can suppose you are writing a program, a process, you can create multiple threads. Okay. And we also saw through that examples earlier how in these threads you can call some function. In the program you are writing, there can be some function f1, there can be some function f2 and so on. Some of the thread may be calling function f1, another thread may be calling function f2 and so on. So, the functions can be called from the threads, and the threads are running concurrently. They are lightweight processes, they share their code, they share their data, but their stack region and heap regions are separate typically. Okay. Now, here using mutex lock, the way you can create these locks for threads, I am not showing the complete program. What I am assuming is that exactly what I said, that when you create a thread using a pthread library, there can be parallel threads. As I said, one of the threads can be calling some function f1, another thread may be calling some other function f2 and so on. They are all running concurrently. So, we assume that one of the functions is this increment count, another function is this get count. Now, one thing you see in the previous example that we took for a shared memory, for a shared memory what we saw, that we have to create a shared memory segment, we have to attach it to the processes, then only the processes can communicate via shared memory. Why this was so? This was so because when a new process gets created, its address space becomes separate, data becomes separate, heap becomes separate, stacks become separate. So, there is no data region which can be shared by the two processes. You will have to explicitly define a shared memory segment and you will have to attach it to the two processes, so that the processes can read or write from that common memory locations there. Okay. But for a thread it is not that difficult, you do not need all such things for threads, because in a thread by definition the data area is shared. So, without doing anything, a process a thread for a corresponding to a process can write into the data region, another thread can read or write from the same data region. Okay. So, you do not have to create any shared memory segment. So, remember that only when you are using processes, then only you need to use shared memory region when you are using fork to create multiple processes. But when you are using multiple threads, you do not need to explicitly create the shared memory segments. So, here what we are saying is that, as I said, that there are two functions f1 f2 I said, let us say increment count is f1, get count is f2. Now, here as I said, we are using the pthread.h library. So, I am not writing the complete program, part of it. There are two variables I am defining which are of interest to us. So, for defining a mutex lock, we are defining a mutex lock whose name is count underscore mutex, and in the pthread library a data type is defined which is pthread underscore mutex underscore t, that is the data type corresponding to a mutex lock. So, I am defining one mutex lock whose name is count mutex, and there is a global variable which is defined outside the functions called count. So, essentially what is being done is that this function increment count is trying to increase the value of count by 1. You see, count equal to count plus 1, it is trying to do this. But the other process is simply trying to read the value of count, it is just doing c equal to count. So, this is a critical section problem. there is a segment of the code in the two processes in the two threads where some common memory locations are updated or accessed. This count is that common memory location. So, when you had talked about semaphore, we said that we can use the wait and signal to lock and unlock, but using mutex locks you can similarly we can do lock and unlock. So, in the pthread library there is a function to create a lock, there is a function to unlock it. So, when you want to lock it, count mutex is the lock variable you have created, you are calling pthread mutex lock address of count mutex. So, count mutex let us say it is set to 0, initially it was 1, it is set to 0, 0 means it is locked. But similarly, when you do an unlock, pthread mutex unlock with the same variable, the value of the variable will become 1 let us say, which means unlock. So, using one of the calls you make it lock, other call you make it unlock. Now, if it is already locked and if I try to lock it again, the process or the thread will get blocked there. The thread will not proceed until the other process which is holding the lock unlocks it, only then you can proceed further. So, you see here the critical section part, this count equal to count plus 1 is protected by this lock and unlock, lock before, unlock after. Similarly, for the other function corresponding to the other thread, here the critical section is this c equal to count. Here again there is a lock before and an unlock after, and after that you are returning the value of c in this function, because it has a return value long. So, this example simply illustrates that how we can use this mutex locks as part of multi-threading to protect some shared memory segments, some critical sections from getting updated by two processes, preventing rest conditions from happening and so on. Okay. Now, the last thing here that we talk about is, we had discussed semaphores, that how we can use semaphores in C. C also has support for using semaphores, because semaphore is a very powerful synchronization tool. It not only does locking and unlocking, it can also do process synchronization as we had seen earlier. It can also count some resources, how many full items are there in the buffer, how many empty slots are there in the buffer, so on. Now, before going into the example code how we can use semaphore, there are a few things I want to say. Now, you recall when you had discussed semaphore earlier, we said semaphore is nothing but a integer variable. So, notationally we write like this: semaphore is a variable, let us say s, s is a variable of type semaphore, but essentially s is an integer variable, and we define two functions on this variable. One is wait, other is signal. Right. Now, let me tell you here, in some textbooks you will find instead of the wait they give it a name P. See, P is the first letter of a Dutch word which means locking, proverbian, means if I have pronounced it correctly. Similarly, signal is written as V. So, whatever we are saying as wait and signal, in some books you will find they call it as P or V, they mean the same thing. Now, I gave an example earlier, if you recall, that suppose there are two semaphore variables S1 and S2, both are initialized to 1, let us say, both are initialized to 1. In one process P1, we do a wait on S1, then we do a wait on S2. Subsequently, we will be doing signal after that, but in the other process P2, suppose we have reversed this order, we have done this wait S2 first and After that we have done weight S1. Now, here what we told, if you recall, that the processes are concurrent. So, any process might get stopped any point in time, other process can resume. So, suppose P1 is executing, after executing the first this weight S1. So, S1 was 1, the value of S1 has become 0 after this weight. So, at this point there is a context switch and P2 starts executing. So, P2 will be doing weight S2. So, S2 value will also become 0. Now, P2 is trying to execute weight S1, but the value of S1 is already 0. So, P2 cannot proceed, P2 will block. Similarly, when you come back to P1, P1 will try to resume and execute weight S2, S2 is also 0. So, P1 will also block. So, both these processes P1 and P2 are blocked mutually. This is a scenario which is referred to as deadlock. So, if you are using such individual semaphores and if you are not careful, then such deadlock scenarios may occur. Now, the question is, what is the way out? Well, one way out, well, I may tell you that when you write your program, be very careful, do not change the order of these weights and signals. But you see, as a programmer, see, it is not necessarily true that the entire program will be written by a single person. Maybe one part is written by one individual, other part is written by another individual. So, there is always the possibility that they have changed the order of these weights, and if such thing happens, this kind of deadlock can be a possibility. So, what is the way out? Well, one solution you can think of like this, that well, although we are using two semaphore variables S1 and S2, let us define them as being part of a group. Like we are saying that S1 and S2 is a pair of semaphores which we would not be looking at separately, but as a group. So, when you are saying that I want to wait, call a wait, I am saying I will be calling wait for both S1 and S2 together. If both S1 and S2 are available, that means the values is 1, only then this wait will execute, otherwise this wait will not execute. Similarly, signal, you will be doing signal on both S1 and S2 together. So, if you do it together, then this deadlock situation will not have happened. So, only one of P1 and P2 will find that both S1 and S2 are 1. That process will be able to execute this wait on this group S1 S2. Both S1 S2 will become 0. So, the other process will be waiting, this process will complete, do a signal operation on S1 S2, again they will get unlocked, the other process can continue after that. Okay. So, in Unix or Linux, the semaphore that you can use, one of the libraries that is available, supports this kind of semaphore groups. Let us look into the code now. Well, here for semaphores again you have to define some header files, like IPC inter-process communication, you have to include IPC, and in addition for semaphore you have to include this sem.h. This is a header file where some of the semaphore variables are defined. Now, for semaphore, for every semaphore you are defining some kind of a structure. You know, in C you can define a structure which is a variable which consists of a number of components. For example, a student in a class, it is a variable, it consists of a component roll number, a component name, a component let us say marks and so on, right. So, here what you are doing in this header file, some structure is already defined, structure semaphore buffer sembuff. We are defining two semaphores psembuff and vsembuff. See, the name implies one of them is used to perform a P operation, wait, other will be used to perform a V operation, which is signal. So, P means wait, V means signal. Now, here within commented block we are also showing here that what this struct SEMBUF actually look like, what are the components of that structure. You see inside that structure there is one variable called the semaphore number. Every semaphore has a number, and what kind of operation you are trying to do on the semaphore. Are you doing a +1, -1 or what kind of thing, and some flags you can specify some additional things using some semaphore flags. Okay. So, these fields will be used in this code later on. Let us see. This is my main function. We are defining some variables first, second, count, and there is a semaphore ID. Like you recall, for shared memory we had defined a shared memory ID. So, exactly similar here for semaphores we are defining a semaphore ID. First thing what we do, just like in shared memory we had created the shared memory segment first. So, here we are creating the semaphore first, and for the sake of example we are creating a group of 2 semaphores. There will be 2 semaphores which will be created. Okay. There will be 2 semaphores, first and second. How we do that? We do that using this semGet function call, semaphore get. Semaphore get, we use some semaphore key, same key. Here I am not showing it, but same key you can use any unique value. The second parameter denotes how many semaphores are there in this group. If it is a single semaphore you will write 1, but now I have said we are taking a group of 2 semaphores, it will be 2. And just like shared memory, you can specify something IPC create, which means if this semaphore is not existing already, create it, create a new semaphore, and these are the access permissions. 7 means 1, 1, 1, read, write, execute, all kind of permission you are giving to everybody. And we want to initialize both the semaphores. Okay, for convenience let us call the semaphores as S1 and S2. Normally when you use it for locking to protect critical sections, the semaphore variables are typically initialized to 1, right. Let us do that first. Both the semaphores we initialize with 1. How do we do it? You see there is a init array which was defined of size 2. Both init 0 and init 1 we initialize with 1. Then this semCTL is a very general function call. All operations we can perform using semCTL. semCTL we specify that same semaphore ID that returned from semGet. We specify how many semaphores are there in the group. Set all means this, you set all the semaphores with the values, what values? Init. So, init 0 is 1, init 1 is 1, you set both the semaphore values with those initial values. Just to check whether the semaphores have been initialized correctly, we call semCTL again with a get all option. Get all means read the values of the semaphores, and after reading, where do you keep it? You keep it another variable array called out. You see out is also an array of size 2. Then using printf you are printing the values of out 1 and out 2. So, you will see that the values will be printed as 1 and 1. Now, there are 2 semaphores, they are numbered as 0 and 1. So, first and second we just initializing them with that value, first is 0, second is 1. Now, let us see some operations. We want to carry out P and V operations on the semaphores. Just an example, I have not created 2 processes using fork. In general you can do that, but I am just showing how you can write the P operation in a code, how you can write the V operation in a code. Okay. For P operation, you recall you had defined a variable called P SEMBUF. Similarly, you had defined a variable called V SEMBUF. For a P operation, normally what you do? A semaphore value which was 1, the value becomes 0. That means, you are doing -1. Similarly, for V operation you are doing plus 1. If a value is 0, it becomes 1. So, to get ready for the P operation, what you do in PSEMBUF, there are some fields I showed SEMOP, SEMFLAG and others. In SEMOP, I specify the value -1, which means what kind of operation you have to do? You have to do a -1 on that semaphore, subtract a value of 1, okay. And flag is same, and there is some flag, same undo. You can keep it, you can undo it, the operation later on if you want. There are a number of flags that can be defined. Similarly, for V operation, you are going to add some value. So, here the SEMOP is plus 1. Okay. Now, what I am doing, this code in a for loop which is running 10 times, I am doing P operation something, then V operation 10 times. So, what I am doing, this is the for loop which is running 10 times, this is the P operation I am doing, and this is the P operation I am doing on that group S1 and S2 together. Just see how you are doing. PSEMBUF dot semnum, semaphore number first. You are doing a semaphore operation, SEMID PSEMBUF 1, SEMBUF semnum second, semaphore operation SEMID PSEMBUF 1. This SEMOP will define the operation that we are trying to do. Then after this you can carry out a SEMCTL operation to again read the values of the semaphore using getAll command. It will store in a array, out array. You can print those values. This will be actually out, not out array, just out. So, you are printing out 0 and out 1, and you are printing the value of count. Let us say count is part of the critical section. Similarly, after you are finished, you will be carrying out VSEMBUF on second and first both the semaphores. You will be doing SEMOP with this structure VSEMBUF. So, plus 1 will be added. So, this is roughly how you can carry out the semaphore operations in C, like you are creating semaphore, defining the P and V operation, specifying how many semaphores are there in the group, how you create a P operation, how you create a V operation, and at the end when you are done you can remove or delete all the semaphores. SEMID was the semaphore ID, there are 2 semaphores under that, delete everything. So, in this way your entire semaphore again gets deleted. So, you see whenever you write a concurrent program in C or C++, let us say, there can be multiple processes, there can be multiple threads, where you need to provide lot of synchronization using the different tools. Some of them I mentioned, but there are many more. So, these tools you can use for synchronizing among the threads to protect the critical sections of the code, for resource counting, process synchronization, all the things that are necessary for multiple concurrent processes, you can do all of them. Okay. So, with this we come to the end of this lecture, and also we come to the end of this module on inter-process communication. So, in the next lecture we shall be starting with the subsequent module. We shall be talking about processor scheduling or CPU scheduling, a number of processes which are running on the system. How does the operating system take care of or decide which process will be getting the CPU next? Whenever a CPU becomes idle, some process has to be allocated to the processor. All these things we shall be discussing in our next class. Thank you.